Okay, in this recording and the next recording, we're going to look at some numerical integration. And so we're going to be looking at estimating integrals using numerical methods. Now the first rule that we want to look at, the one we're looking at in this recording, is called the trapezoidal rule. And what it does is it approximates short stretches of the curve with line segments. And as you can see in the picture there, we have some little trapezoids. Some of the trapezoids are underestimates, some of the trapezoids are overestimates. And so when we approximate an integral from A to B, we add up all these areas of these trapezoids that are made by joining the ends of the segments to the x-axis. Here's the trapezoidal rule. So we're going to approximate the integral from A to B of f of x dx. We use this rule. Now notice the delta x is your b minus a over n. That tells you the width of each one of your trapezoids. Okay? And we're going to do y sub 0, which is the y value at the first point, 2 times y sub 1, which is the y value at the second point. And so this is a little bit different when we did left and right endpoints, because we actually use both the left and the right endpoints. The y sub 0 is our left endpoint, the point at A, and y sub n is the point at B. Now let's take this example. We want to use the trapezoidal rule with n equals 4 to estimate the integral from 1 to 2 of x squared dx. And we know how to find that integral using the fundamental theorem of calculus. So first we're going to make that estimate, and then we're going to go back and we're going to use the fundamental theorem of calculus to find that. Okay? Now what the trapezoidal rule tells us is first we need to find delta x. Now delta x is the length of our interval from 2 to 1 divided by the number of partitions we're going to have, which is 4. So our delta x is 1/4. So what we need to think about is we're going from 1 to 2 in intervals of 1/4. So the first one's going to be 5/4. 1/4 more is 6/4, so 3/2. 6/4 plus 1 is 7/4. So what we're going to be looking at is we're going to be looking in 4 spots. Okay? Now, the rule calls for us to look at the beginning and at the end. And what we do is we take our delta x, which is 1/4, and we divide that by 2. Okay? So the first part of that formula was delta x divided by 2. Now, we find the y value at 1. So since this is x squared, that's going to be 1 squared. Plus, and we do 2 times the next y value, and that's going to be 5/4 squared. Plus, and we do 2 times each of the interior partitions, so 2 times 3/2 squared, 2 times 7/4 squared. But then when we get to the end, other endpoint, it's just 2 squared. Okay? Now here, 1/4 divided by 2, multiply top and bottom by 4, and you'll have 1/8. 1 squared is 1. This is 2 times 25 over 16, plus 2 times 9 over 4, plus 2 times 49 over 16, plus 2 squared is 4, or 1/8 times 1 plus 25 over 8, just canceling here, plus 9 over 2, plus 49 over 8, plus 4. So just go ahead if you want to and type that into your calculator, and you'll see you're going to get 75 over 32. Okay? It might help us to have that as a decimal. 75 over 32 is 2.34375. So this is what our estimate gives us. Using the trapezoidal rule, we find that integral from 1 to 2 of x squared dx to be 75 over 32, or 2.34375. Now we want to compare this to the actual estimate, or the actual value, which is the integral from 1 to 2 of x squared dx. Now remember what we said earlier. You take the antiderivative of x squared. Well, I need to add 1 to the exponent. And then I need to do 1 divided by n plus 1, which is 1/3. That way when I do 3 times 1/3, that will cancel out. And I'm going to do that from 1 to 2. So we find our antiderivative. We plug it in at the upper endpoint minus, we plug it in at the lower endpoint. Okay, so that's 1/3 times 2 cubed is 8, 1 cubed is 1. So I have 8/3 minus 1/3 is 7/3. Now if you think about 7/3, that is the same as 2 1/3, or 2.3 repeating. Okay, so our actual integral is 2.3 repeating. What we got with the trapezoidal rule using just n equals 4 was 2.34375. Okay, now this just gives you a kind of a picture. You can see we found each one of those little areas in there. We've got, to find that, we added all of those up, plugged those into the formula, and we got a very close estimate to the area.